Hello everyone. So today we are going to play with parameters. So yesterday all of you ran the benchmark case and all of you ran exactly identical parameters. So today we are going to use that run and all of you will run a different parameter and we're going to see how that turns out. So today you're going to change a couple of parameters and also use a restart file. So yeah, the login from yesterday, I guess you're already logged in. Compile the code. So these are the parameters that we're going to change today. The Rayleigh number, which is a measure of the buoyancy driving of the system, and the magnetic Prandtl number, which is a rough measure of the conductivity of the fluid.
Pointer?
Yeah. And then, after we have changed the parameters, we collect all the results, the time average values, and we try to construct something like this. Changing Rayleigh and magnetic Prandtl, and we look at different quantities and how they vary. Before we proceed, maybe note down the parameters that you will use. So
now it's fine.
You should be able to use this. Yeah. Presentation.
Yeah, the presentation, yeah. What? Ja, das habe ich eingetippt. Also da zum Beispiel. Oh, I have my task.
TM4. Yeah.
He's the unlucky one, right?
Well, you have to boring.
It's PM is PR Mac here?
Yeah.
Okay.
So till magic 8, have you noted down your parameters somewhere? Just note down your own parameters. Alright? Yes, no, just your own.
Sure.
Just the two of you. Alright, alright. And these are from 9 to 16.
Yes, question. Because we have in the benchmark file, we do have the bench. In this script, because in the directory before, we have also specified the bench. So is it that one or that one?
So I will ask you to the input bench and new directory. You will create different directories.
So the results are in the different directories.
Yes. All right, everyone noted this down till magic 16. Okay. So now go to your home directory and each of you create a directory named like this. So this is the Ekman number, 10 to the power minus 3, then corresponding relay and PM. Yeah, so each of you on each computer you'll have two directories corresponding to your two parameters. Yeah.
Just like go back one, so if we because we didn't take both.
Ah.
It's just like because we have two.
Yeah.
That's a very short.
So this one.
Yeah. Okay.
Okay.
Fine. You both need
Yeah. So once you've created the directory, copy your executable from yesterday over there, and also copy the input name list from yesterday, and the restart file that you generated.
Make sure that you don't forget the last step here, because the idea is that you restart from the solution from yesterday, so really make sure that you copy your restart file here.
Geht da nicht, das wird ganz schnell fertig sein, wenn noch ganz weit unten bleibt. Also ziemlich viel verlieren. Ja, so. So. Ja.
So is everybody done with this?
Ja. Oder? Ja, aber gibt nicht drauf, dann kann ich nicht runterladen.
Now we start. Now you open up the input.nml file, the input name list, and we start changing some stuff marked in red here. So first you change your tag from test to something like this: relay number, magnetic random number, and your number of time steps. We're going to run them much longer today, and your runtime. So the idea is that you start your runs now, and when you return after lunch, the hands-on session in the afternoon, we look at them, and hopefully they would have completed by then.
You can also then try an interim signal.
Yeah.
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 Aber das Back.
Nee, kein so.
So I can show you how the manual makeups
Oh, this doesn't have Git.
What? Doesn't have gate. What?
We never installed it here, so
You can't install it. We're supposed to be there. Gate.
Did you log in on the node? Did you log? Ah, yeah, okay. No, you did an SSH on the node, right?
oh, we didn't SSH on the node. That was
You don't need to clone the code anymore, I think, right?
yeah, I
It should
thought
be
so
there.
too.
Yeah, yeah. So you need to log in as yesterday because I guess you logged out. So minus capital Y. Minus capital Y. Should be at plus whatever your number is.
You remember where you're supposed to?
No, we haven't logged in. We
Yeah.
have used the laptop.
You have never logged in.
Oh wait.
Well, if you want, there are some free machines. Fun there. There are 2, 3 there. So
What is the password there?
workshop W.
So yeah.
Magic 03.
Yeah, you're supposed to log in.
Magic 3, Magic
Atlas.
03. Yeah, I go to Atlas 03.
So okay, Atlas 04.
03. Atlas 03 is here now. Right?
No.
No. Sorry, yeah, it's 2. Half of 2. Yeah.
Yeah, two.
First half of 2.
Okay.
Ihr müsst Magic 03 at Atlas 02 machen.
Ja.
Das ist euer.
Magic
Also als Zahl.
Ja, wir sind eigentlich schon Magic 03.
Habt ihr at Atlas 02?
Das Add hier. Was
Ja.
ist denn das für eine Tastatur?
Okay,
Englisch.
Was ist denn das für ein Layout?
Alright, everybody done with this part? Just a second. Yeah. Okay.
Just a question, because we changed it.
So, well, basically the time step should just multiply it by 10, I think, as compared to yesterday. So here.
Also Englisch ist eingestellt.
Englisch, ja.
Because we changed it before.
Make sure that you increase your runtime, otherwise it will stop after an hour or 2 hours. Well, even if you don't do it, you can still rerun, right? So it's just easier if you follow this thing.
So everybody happy
No.
with this?
Permission denied.
Permission.
Come on.
So which?
Okay, that was way to go, right?
Atlas 2 is supposed to be Magic 3. Yes. So.
Okay.
That sounds right. Did you change your password or what?
I remember.
Das wieder eingegeben.
3 is supposed to go on 2, right?
Yeah,
Well,
That's what
2.
your slide says. Yes.
Workshop aber eine Null eingegeben.
Yeah.
Okay. Well, then I have no idea what's going on. So,
Honestly. Sorry, guys.
Anyway, for the others who have completed this part, we go to the next part of the name list, and the most crucial part, change the relay number and the magnetic Prandtl number to the values that you had noted down.
Okay.
Wait.
Yes, no.
Or they can send the init down on the
Yeah, this the blue stuff is supposed to be removed.
Yeah, or they send the init down.
Also the info.
Yeah, maybe we should say both options. I mean, sometimes I like it.
Yeah,
Reminds me of work.
I never specified.
So init V1 goes to 0.
0, 0.
No, just the init ones.
Yeah, because
I mean, I really
that
took
we
it.
don't
Care.
oh, yes.
So you have to, explain the system options. Either you want them. Yeah.
Yeah, so with the restart condition, so we changed the restart condition. Yesterday you started with a guessed disturbance, basically, something which was true or close to the solution you want to end up with. Now we start with the restart file that with pure stress series, so the total information is there, and we know it's a valid solution for the dynamo, but not at the new parameters. There will be some transient. Basically, you have two options now. You can leave. You set this to true. That means it will read the restart file that you gave here. If it doesn't find it, it will tell you and stop basically. And then on top of that, if you want, you can add a disturbance. So if you leave these other parameters like they were, it will take the restart file and add to that the disturbance you have used yesterday as a starting condition. Well, if you don't want to use that, add it. You can either set the init B1 to 0 and the init S1 to 0. Then it wouldn't do anything. It wouldn't add anything to the restart file. Or you can just delete these lines because the default is not using these, right? So that's the two options you have. So it's simpler to just set the init values to 0. Then you still have the lines in there in case you want to change it back. It's more easier. And anyway, maybe at this point I could also say, in case if you don't remember all these options you have with the code, I mean it's somehow difficult, all these name lists, everything is written in each log file. So if you look at any log files, all the name lists are there with all the default values and the values that you change. So in case you don't remember all these were called and which you used, look into any log file.
So, jetzt machen wir in dem Verzeichnis nochmal das Verzeichnis. Template E-.
Alright, everybody happy till here?
So, und jetzt brauchen wir da drin das Input.
Next we come to the log step and the number of graphic files that you want. Since so the log step is the number of time steps after which it writes to an output file. And since it's going to be a really long run, I suggest that you maybe change this to 100 so that you spend less time writing to output. So this was 50 in the name list that you used yesterday. I suggest you change this to 100.
Yes. So you took the one from yesterday. First you create the directory.
Yes, that's what we did here.
Okay, then you take the name list from your benchmark.
Samples.
No, the one that is okay.
The number of graphic files you
Okay.
can,
So we
you can
need
keep it to
to
3.
Yeah, but you can.
So it writes 3 graphic files during the whole run. And the number of spectra,
Can I get the normal terminal?
change
somewhere?
it to 5 so that we have 5 snapshots of the spectra during the run.
Here.
And the rest is the same as
Yeah,
yesterday.
-3. So the good thing is you just clone magic right now, right?
Yes.
Yeah. You didn't compile yet?
I did compile.
Without the OMP, right? So you do the CMake -D use OMP. It's just if you don't disable it, it might just try to use the OMP.
But it did run try.
No, it runs. It will run. The thing is that we have a limited number of processors. You don't want to collide with your neighbor, so it's safer to disable it. That's the only thing. Start here. So the CMake should be there. Yeah. So that's why I just.
So everyone happy in here?
I mean, in practice, when you run on a normal cluster, you don't need to disable it.
Now, as yesterday, export this variable so that you don't collide with your neighbor on the same node.
Anyway,
That's still valid. We export, well, if
if
have
you
not
didn't,
logged out.
if you haven't logged out, then it should still be there in principle.
yeah, but
But it's better to do it again.
yeah.
So we were supposed to start from the solution you ran yesterday. You didn't run it, but the good thing is that there's a simulation you ran yesterday is part of the AutoCAD of the code. So like there is a sample directly as an autocad. So so the magic by example, which will bring some example in there.
Yeah.
And there is one called boost that benchmark that never separated. So it's already reaching the final state. And there is a source variance in there. So it should, in principle, you could use that one. I think it's going to be exactly the same as what they have.
Each node has
Actually, it's even longer than what they did, so it might be even better.
but because, so for this resolution, 8 cores is
Yeah,
faster.
this is some powers right there, provided the technology. Okay, and then the name list. Copy it from the home directory then.
So after you've exported the variable, run the code
So-
with the no hub command in front so that your code is not interrupted. If you log out by accident or
And
something.
what's your relay number? I think you had two values.
Yeah, 2.5 and
Okay, I'll go for 2.5. Okay, so 25, E5. Yeah. So you need a bit longer here, so 5,000, and we put 5 hours, 7 minutes, roughly until the afternoon. Okay, so you want to have this relay number, so you just change the value here. E5. And what's PM? Put it here now. So it's going to be the extension of your file. Might be helpful for you. So 5 was there already. Okay, and you want to start. So this time you want to start from reading previous file, so which is actually the file I put in the directory here. So I don't need to change the name, it's already named like that. Just need to put that through. Cool. Okay, now this part concerns the possible initial magnetic field and initial temperature fluctuation you may want to put. The thing is that here you're reading a field, so you don't want the fluctuation on top of it. So the two things you can do is either you suppress this one line, then it won't initialize anything, or you just put 0 here. Basically, so and then you have the same thing, so it doesn't, by default, if you put 0, it doesn't initialize anything, it's just reading. Okay, it's up to you. The thing is that if you keep the line, then it's easier when you want to rerun something that your line is already there. If you suppress them, you have to type them again. So I tend to rather use 0 because it's more, I find it more convenient because your options are already here, rather than suppressing them. But, you know, it's the same when I put move equal false, I can simply remove the movie, but you know, it's in a way simpler if you have the option there. Okay, so what else? So as Ankit said, I mean, the run is going to be pretty long, so you can increase slightly the log stack to get 100. So instead of writing every 50 time step, you write down to 700 time step.
the G file.
No, it's not the G file, it's time series.
Oh, it's
So
time
kinetic
series.
energy, and so forth. Because I mean, the thing is that if you make this number like 1, let's take something stupid, like you make 1 here. So it means that the code will write output every time step. And it's going to be a big overhead because you are doing a lot of output on the hard drive. You should never do that because it's slowing down the code. So on the other hand, you don't want to put a too big number here because you want to have some information on what's going on. So usually 100 is already something decent. So this is DT max is the maximum time size you have here. So your Ekman number is 10 to minus 3. So DT max is 10 to minus 4. What does it mean? It means that basically the maximum time step is a tenth of the rotation period. So you'll do it. In other words, you'll do 10 times than the one rotation period. But that's the maximum value, and as you will see, when you're going to run, this number will decrease maybe to 10 to minus 6 or 5 10 to minus 6 or so. Which means that n log step in 100 brings you back to values around 10 to minus 4 something. You already have outputs every rotation period or something like that. So it's already quite dense. Right? Usually.
What happens if you increase the time at the Courant criterion? So that you would get bigger time steps?
No, I mean, there is no, well, the thing is that Coriolis force is not treated implicitly, so you cannot go faster than the rotation period. So even if you put like whatever here, 10 to minus 2, should be 10 times the rotation period, the code wouldn't use your value here. It would automatically degrade it to 10 to minus 3 or something lower. Okay. So the number of graph file, this is the number of graphic output I can perform, whatever. This is the number of restart files, so you need only one at the end. And this is the number of spectra, so I increase it because it's, I want to show the output here later on. So maybe I put 5. And it looks good. Okay. Now we are here. So yeah, just to make sure, now we need to copy the executable we compiled, which is the file before. So in magic, build, magic, let's copy it here. Okay, you are happy with that. And then you have to export this variable. So practically, if you run to a cluster, you don't need to do that. You only need to do that simply because you are sharing the nodes and you're running directly onto the computational node, which you would never do on a cluster.
Yeah.
I mean, usually you have a batch system, you write your script to submit and go into the queue and whatever, and you don't need that. It's handled automatically by the queuing system. But here, it's just to make sure that you don't use the same CPUs as the other guy using Atlas 2, which is usually Marcus or Katina there. I don't know. So you just export this variable and you just put it to the number of MPI you want. So which is,
but if you run MPI with N8,
yeah,
doesn't it guarantee that you only use 8 CPU?
No, you could use, it guarantees that you use 8 ranks, but it could simply use 50% to, well, you know, you can divide your CPUs into whatever number of things. So MPI by itself could say, okay, I have 4 CPUs, this guy asked me for 8, so each CPU will take 2 tasks, yeah? And it's going to be, so that's precisely to avoid this thing here. So shared context. Just to make sure that I don't use any typos, otherwise that's definitely a complaint. Yes. Okay, and I think you're ready. So N8 input. So if I do that, the thing is that it will just, well, it will be locked like that, right? And the run will have the information displayed right away here. So what you can do is use the no-app command, and then the job will go into the background. And then you put the 9% at the end, if I find it on the keyboard. Here, 7. And then the job will just go in the background, and you still have the end here.
Create an output file.
Yeah, it will create everything as usual. It just won't display anything here.
We console log. Oh yeah, no app.
And here you're here. So let's see it's starting. So let's start. Yeah, wait a little bit. Oh, something went wrong. So something went wrong. In that case, I will run it right away. don't know what's wrong. Okay, so something went wrong.
Okay, now it's better than the way.
So I tried right away now. Okay. Oh, format.
Yeah, I know.
Yeah, the thing is that, okay, so there's a little issue with that. Yeah, inform. Okay, I see. Yeah, it's just so it's a very old version of file generated by me or Johannes in a very old version of the code. And the thing is that there is not, so there is not how it's called on the registry of it, right? Not the one you use. There's a very old format, and then you have to change this end formatting to 5 to make sure I just check. That was the reason why it locked. It's nothing really serious, but check. It's inform file, yeah. So it means it's just its old format, which is now deprecated, but just for backward, you know, not touching this file, I just kept it as it is. I mean, the others won't want to do that because they generate their own stuff. So let me just check the run. You see already the timestamp decrease. So okay, I just kill it and then I submit it in the backward and the back. The back. For now, let's check whether see? Right. Okay. Okay, so I leave you with the second one, right? You have a second job to submit. So this was the first PM, so you have to create another directory with the other values that you wrote down somewhere. So
We have more than one value?
Yeah, two runs, I think.
Yeah, 2.5. Ah, okay.
2 jobs.
So it was something at one point, yeah. Just grow up
Wenn wir das auslegen als
and the other one as well, yeah.
Did you update? No, but I mean, anyway, I can set it again. I mean, this topic, you have the right set of just load it this morning. And I mean, I see the way it's coded, it's like allocating to an
And then there are some zeros, right? So if you do like log 1 to n, then you're doing 0 to 0. Some compilers will some like So can you do a talk for one of the to see whether you're really using
Yeah, but sure, when we reach it, we will do that, yeah.
Just to make sure that you go not running, half 50% or whatever.
Yeah.
So that's the way to check whether the variable was correctly exported.
Processes for
Yes, so you're running the machine. So 4 jobs.
no.
Yes. So you still have 16. It's 48 CPU machines. Yeah. So what you can do is maybe check doing a talk to see whether so we're running, I guess there are, but you would be 100%.
In der Business-Gleichung.
Das G von der Cousine ist. Der Gravity.
Ja,
Gravity.
Gravity.
Gesagt, ne?
Mhm. Ist das das R, mit was das multipliziert wird, ist das einfach das R aus den nichtdimensionalen Shell?
Ja.
Oder ist das immer, geht das immer bis maximal 1?
Also das ist einfach, naja, Uli hat das kurz erwähnt. Also man muss sich überlegen, wie man die Gravitation beschreibt. Und da gibt es verschiedene Möglichkeiten. Also entweder, wenn du einen Stern machst, ist typischerweise, du hast alle Masse im Zentrum. Und dann verhält sich Gravity wie 1 über R Quadrat, also über N Quadrat. Die Option gibt es auch. Und wenn die Masse homogen verteilt ist in deinem Körper, dann ist es einfach linear mit R. Das ist für die Erde eine gute Näherung, sage ich mal. Es ist nicht perfekt, aber es ist eine relativ gute Näherung. Das heißt, es muss nur irgendwie linear mit R zunehmen, wenn du tiefer reingehst. Und dann geben wir praktisch außen die Gravitation vor. Ja. Und, nee, die muss ja abnehmen. So. Und, nee, ja, nimmt ab, wenn du weiter reingehst. Und sagen einfach, das verhält sich dann linear mit R, also nimmt entsprechend ab. Ja, und das wird dann so, kannst du dann so nehmen, dass du praktisch außen, wo wir ja die Gravitation messen können für Planeten oder für die Erde einigermaßen wissen, dass du da den richtigen Wert erreichst. Und dann nimmst du aber eine lineare Abhängigkeit an. Das ist eine einfache Möglichkeit. Das ist nicht perfekt, aber das ist eine relativ gute. Du kannst aber auch, in der neuesten Codeversion kannst du auch Profile vorgeben, wenn du das möchtest. Also dichte Profile und daraus kann man dann natürlich auch die Gravität ausrechnen. Das geht auch. Ja, und davor steht dann ja praktisch diese Rayleigh-Zahl.
Genau.
Und da
die muss ja richtig skaliert sein.
Die muss richtig skaliert sein. Da steht dann halt die Gravity drin,
genau.
Wie du sie normalisierst. Ne? Und dann sagst du, okay, der Rest ist dann nur noch die radiale Abhängigkeit.
Okay.
Of course, it's the password is the same for all. Right, no, because afternoon I need to collect results from all of them. And I need to dump them on the same folder, so it's easy for me to just go and move. Okay. From the results are located on the Atlas nodes. Yes. But they will get the results just on one screen. They will one option would be just like SCP from their folder to yours. Yes. So. Check all our we could set up a folder on that's writable for all for the whole world, for example. This would be possible in all just SCP based stuff. So there's no option to get them closer together since they are spread over with local counts. So inside the scratch folder, dump or whatever, and they can dump their stuff there.
With each of these clients.
Well, if nobody changed the password, you could also just SCP the stuff. Or each node. Copy it from there. I know the password. So if nobody changed the password, so or you can fetch the stuff to your folder, so they don't have to access your folder. That's not the to check your password. Alles ist auf das eine Problem löst. Ein kleines Problem ist. Haben wir die Tastatur eingebaut. Danke. Das ist interessant. War ich schon. Ja, du siehst doch so frisch aus. Ja. Aber die Euro, das eigentlich war schon ein Problem.
Yeah,
trailing. I think it's just the 1-to-1 translation from English or whatever.
Okay. Yeah, Anke is supposed to show it here. Comes the button. I mean, I have some snippets here. Yes, physical.
I don't want
Okay, so while the code is running, we talk a little bit about what the code is actually doing and how it's structured. Yesterday, I introduced, magic by words, and we went through a few of these points here. What is left basically is down here. So, what does it mean that metric is a pseudo-spectral code? So, how do we transform between the grid representation and the spectral representation? And then, what is the actual time integration that magic uses? And just to remind you, you find everything online. And now we will also go into the code and look at a few of the files to give you a rough idea how the code structures and what's going on in the individual files. Yes, well, again, this manual, and you can read everything later if you want. So here, if you go to the contents, here's numerical techniques. So I'm going to talk about some steps that are also explained in these things here. So yesterday I also showed you the flow chart of magic. We talked about basically the ramp up stage, and then the final stage and some output. And now, as I said yesterday, this is basically the work stage. So this is the time integration. And now we have a look a little bit into what it's done here. So we come into this with the fields from the start, the initial field, so the start condition. And then the whole purpose of this block is basically to update the field. And what the most complex part of this is calculating the nonlinear terms. So this is advection u dot grad 2. This is the Lorentz force, curl B times B. This is also the dynamo term itself, curl U cross B, and advection in the entropy equation. So these are the nonlinear terms, and they are really complicated to calculate. And magic spends most of the time doing that, and it actually calculates these terms on the grid. So each grid point, the physical grid, it just multiplies the two quantities, so U and B and whatever, B squared, current and B and whatever. But the actual time set, so the update is done in a spectral grid, so a spherical harmonic representation. So we need transforms to go from one to the other and back. And we're going to talk about that a little bit. So how does the grid look like? So the grid is, well, a little bit special. And it's made special because we use certain, well, polynomials to represent our solutions. And they are chosen according to, well, two considerations. First of all, it should be close to what you need, so in terms of representation. And it should also be efficient. So efficient transforms from the grid to the spectral representation should be available. And when you think about this a little bit, you come up with this solution. So in azimuth, it's very simple. So in the longitudinal direction, you basically just have equidistant grid. In latitude, from pole to equator to the other pole, it looks like equidistant, but there is a slight shift, so it's not quite equidistant. So if you choose the grid points to match what is called a Gauss-Legendre grid, and I'll come back to that a little bit. And then in radius, you choose a very special polynomial, so called Chebyshev polynomials. And the grid then, which is you best use with these polynomials to get an efficient transform, is not equidistant at all. So this is shown here. It becomes denser towards both boundaries. And that is a good idea because at the boundaries you may have to resolve boundary layers. So this grid not only leads to an efficient transform, but it also resolves better when you need high resolution. Okay, and now, so how do we actually transform? So first of all, as I said, we use spherical surface harmonics in the latitudinal and longitudinal direction. These are defined like this, for example, where these are called Legendre polynomials. They describe the latitudinal dependence, and then it's just an e to the IM5, just a Fourier dependence for the longitude. Well, and then you have to choose some normalization, and what we do is we use what we call fully normalized spherical surface harmonics, which just means if you integrate the product of two with different L and M over a spherical surface, you end up with either 1 if two L's are the same and two M's are the same, or 0. So these are chronicle deltas here. Okay, and now the question is, how do we get from, for example, a spherical harmonic representation of, let's look at G, for example. So that's the magnetic poloidal potential G, just as an example. So the spherical harmonic representation would just be all the coefficients that you need to represent this. And in theory, you need an infinite number, but of course you truncate somewhere. And we truncate, we just call it L max. So it's maximum degree, spherical harmonic degree, where we truncate. And then the spherical harmonic order just goes from minus L to L. So then if you have this representation, it's a simple matter to go from the spherical harmonic representation, from the coefficients, to actually the physical grid representation. And these coefficients, you can see, they depend on radius in this example. So in radius, we always have that grid in this example, right? So you just multiply the coefficients with the spherical surface harmonics, and you sum over all these different contributions, and you end up with the grid representation. So that's fairly simple. And well, then how do you go back once you have the grid? Once you have the grid representation, so for example, you start up with having G, which is just defined on the grid, so on radius, on latitude and longitude. You need a way to go back to the spherical harmonic representation. So what you do is first you do basically this step. So, and this, if you look at it, is just a Fourier transform. So this here is just the e to the minus I and phi, and then you just integrate over all longitudes. This is just the Fourier transform. So here you can use fast Fourier transforms. And then you need this additional step where you basically integrate over the latitudes, right? Multiplying the P and M. Well, this is also an integral, and what we actually do, as I said, I mean, in longitude we use fast Fourier transforms, and for latitude we use what is called a Gauss-Legendre integration, which is actually an exact integration in latitude if you choose the correct grid points, the Gauss-Legendre grid points, and then you have to weight them in the correct way with this weight W. If you do this, you get an exact representation for the truncation L max, so for the maximum degree you've chosen for your spherical harmonics. So that's a good thing. So you just have a simple sum, easy to compute, but you have to pre-compute those weights and you have to choose the grid accordingly. And that's done in the pre-computation step for magic. It's not difficult at all. look at numerical recipes, I just copied that from numerical recipes. So it's not complicated. So it's an exact integration. That's the good point. So now the question is, how do we choose our grid? So typically we choose, well, an input parameter is what is called n phi tot. So the total number of longitudinal grid points, and then the grid points in theta direction is, of course, just half of that. So because once you go from basically 0 to 2 pi, in longitude and latitude, you go from 0 to pi, so you just choose half the number. And then, well, for this step, actually, as I said, this is just a multiplication of basically the matrix with a vector. So, and that can be done in a clever way. So you just think about symmetries you make use of. Well, just are very careful to make them in a clever way. And we thought we had a very clever way. And I think we had a quite fast transfer, but recently we implemented a transform which was developed by Nathanael Schäfer. It's called SHT, so spherical harmonic transform, and then NS stands for Nathanael Schäfer, I guess. Yeah. And we found that Nathanael was even much more clever than we were. So now this new transform is speeding quite effectively, actually. And that will be released, as I said, in a few weeks, I guess, this new version of Magic. So, okay, and then, well, I told you how we choose the grid points, and then what you typically do is you do basically de-aliasing. That means, well, in theory, what you could do is, if you need the grid points, you have so and so many points, and then you can choose your unknown spherical harmonic coefficients to have the same number. So you have 10 grid points to constrain 10 coefficients or whatever, right? You don't do that. What you do is called de-aliasing. So that means you choose a number of physical grid points which is larger than the spectral representation. And that just avoids of aliasing effect, which means if your system somehow is under-resolved, so you don't have enough grid points, then you end up with having artificial energy in the highest spherical harmonics of your system. You avoid this by basically choosing more grid points, and then you transform to the spectral representation, and then you don't use the last highest spectral modes. You throw them away, basically, right? So these modes could have potentially a problem, but you don't consider that. So that means you're just left up with the good part of your spectrum, so to say, where the under-resolution doesn't matter. Hopefully it doesn't matter. Okay, so that's called the alias. And then for the spherical surface harmonics, there is a rule which is just expressed here. So the maximum degree and order that you use can be determined based, say, on the number of longitudinal grid points, and then you divide this basically by 3. So this is called the triangular rule, and that's what's done in Magic. So you're certain that when you run Magic, it's fully de-aliased. You can show that analytically. You can control this in Magic, actually. So there is a factor, it's called N de-aliasing or something. Or de-alias. Ah, you have it here. N-alias. So you could change that, and then change basically the aliasing. I don't recommend it. Sometimes you do that as you say, I don't need the aliasing, and I save a little bit of time, right? Because I have them a smaller grid basically, but I don't really recommend doing that. It doesn't pay off so much. You don't save that much. Actually. I don't think it's worth trying. But if you want, play around with it. Okay, so this was for the latitudinal and longitudinal representation. And so you could ask, why do we use this specific shell for harmonics? And generally on the spherical shell, it's a very good idea. Because they are a natural shell for harmonics, and generally on the spherical shell, it's a very good idea. Because they are natural eigenmodes of this horizontal Laplacian. And you may remember from yesterday that this Laplacian appears in our equation. That's always part of the diffusion part of the diffusion, for example, equation. So if you have such a spherical harmonic representation, the Laplacian acting on it is very simple. It's just degree L times degree L plus 1 over radius squared. So it's very simple. You know the solution to that. That means you have an analytical expression for important derivatives in your system. And this is exact. That's a good idea. And, well, basically, the reason you have, I mean, in theory, you could solve everything on the grid, right? And if you have finite difference codes or finite volume codes or something like that, they do that, right? So just calculate all the derivatives with finite differences, for example. The disadvantage is these methods are not so exact. And to compensate for that, you need typically much larger grids. Right? Here, we are certain these methods are exact up to the maximum resolution you're choosing, right? But you know at least that. So the advantage is, as I said, you can express now all derivatives in the system. If you have the spectral representation, you can express all derivatives analytically. So this is one example. Another example is here, basically this theta derivative, so the colatitudinal derivative multiplied with sine theta, and you can express this acting on the Legendre polynomial like with a recurrence relation. So if you do that, the result of this depends on two other Legendre polynomials which have degree L plus 1 and degree L minus 1. And then when some known coefficients in front of that, we call them CLM, and the expression is here. It's a little bit complex. This also depends on the normalization you choose for the usual Legendre polynomials. But the point here is it's analytical, it's exact. So, okay. And, well, yes, okay. The next point from here to here is, so if you have, well, if you have such a term, you want to know what is the contribution of such a term for a given degree in order. So basically, as I told you, we solve spectral equations for a given degree in order. So we want to know what is the contribution of all the terms in our equations for a given degree in order. And then we solve these equations, right? So what you typically do, I mean, that's probably most of you know that. So if you multiply from the left-hand side with the Legendre polynomial, and if you care for that longitude as well, you multiply with e to the minus im phi as well. And then, so this is just an example for this expression, right? So you have this theta 2 equal to m. And then you integrate over a spherical surface. And then what you do is you use these normalization conditions here. And then you can screen out actually the contribution that this expression or any other expression makes to the spherical harmonic contribution of degree L and order m. And this is then, because we know the recurrence relation in this case, at least because we know this is an analytical expression that we can write down here and then use to construct the specific equation we want to solve for this degree in order. Okay. So we haven't talked about the radial representation. Why do we need the radial representation? We actually don't solve in the Chebyshev spectral space. But we need the radial representation to get exact radial derivatives. That's the reason. That's the only reason for this transform in radius we use. So as I said, what we do is we use Chebyshev polynomials. They are called Cn here. In the code, they are called Cheb. Right? So simple. And they're defined like this. So it's the cosine of n, where n is the degree of the Chebyshev polynomial, times arcus cosinus of x, where x varies between -1 and 1. So it's basically, you can think of this as cosine theta, which varies between -1 and 1, or not cosine theta, it's actually radius. So somehow you have to map your radius which goes in the code from minus inner boundary radius to outer boundary radius 2 to actually a space which goes from -1 to 1. That's a simple map. You just map that by renormalization derivatives, and then you can use this Chebyshev polynomials. And okay, and now what is useful, as I said already, is if you use a very specific grid. And I've shown you this grid. This is a useful grid because it becomes denser towards the boundaries, and the grid is defined by this. So actually, the grid points are the cosine of pi times k minus 1, where k now just numbers the number of radial grid points, the maximum number being n underscore r, being index r. And you divide this with some normalization factor. And if you plug this in here, these x, because you have the arc cost, this cost just vanishes, and you end up with a definition for the polynomials at the given grid points x, k, which is just a cosine. So that's nice. And if you have a cosine, you can actually use fast cosine transforms, especially a derivative of fast Fourier transforms. These are freely available. They're very efficient. You can't do anything to make them more efficient than these transforms, which are already out there. So no work for you that needs to be done here. So that's nice because you use this specific Chebyshev grid, and then you also have to ask the question of de-aliasing. So do I use more radial grid points than actually the maximum degree of the Chebyshev representation in my system? Generally, you would say it's a good idea to do this, to have de-aliasing. We typically don't do that much. So actually, you remember the input parameters, nr max. nr max is this here, right? So the number of radial grid points. And n sharp max would then be the number of Chebyshev modes. And if you check your input files, you would find that this is only 2 smaller than this one. So we don't do much de-aliasing, just very little. But typically that seems to be okay. But again, if you want to play with that, do it. Maybe a nice exercise. But so far we didn't find much effect. So, okay. So these are the input parameters. I said this is the number of longitudinal grid points. And then basically, you need the same Chebyshev representation for the inner core, where you solve the simple diffusion equation for the magnetic field. So this is again here. And this Mink is actually choosing the longitudinal symmetry I told you yesterday. And then the last one was this de-aliasing in longitude and latitude representation. Okay, now let's look at one example for one equation. So how do we get from the equation, the dynamo equation I've shown you yesterday, to a spectral form of this equation? For example, for the colloidal magnetic field potential, G, we call it G. And I told you yesterday, so to screen out an equation for the colloidal magnetic field potential G, you just take the radial component of this equation, of the dynamo equation, and then you get this. And you see already here, again, is this horizontal Laplacian. And now in spectral space, we know this is just L times L plus 1 over R squared. So simple, right? So you can see it's a good idea to use a spherical harmonic representation. Now, what we do is now, the next step is we plug in actually the representation in spherical harmonics here for the G. So this sum over all L and M, and then G, L, M is then here. And Chebyshev harmonics of degree n. Right, so that's what we did here. That's all we did. And now the equation then looks like this. So I plugged all this in here, right? So the Chebyshev representation, or the fully spectral representation. So this is actually now an equation for a given degree and order, right? But here's an additional trick. Actually, this actually means we need a sum over all Chebyshev polynomials of n. So we basically multiply this here with the Chebyshev polynomial of degree n. And that means this is actually a radial equation, right? So you remember, I can write this down again. So it's simple what that is supposed to mean. So this is the Einstein summation convention. So if you have the two same indices, it just means you have to sum over them. So that actually means what I have there basically is, think of this as this. So I have basically Cn, Gn, and this for all Ln. So L, M, N. Right. So you think of this as this is what it means. So this is an equation, and this the Cn is basically, it's not written here, but this is at a given radial grid point. So it's a Chebyshev polynomial of degree n at a given radial grid point. So this is a spectral equation at a given radius r. That's what it says here. And I already said, so this operator here gives you basically this L times L plus 1 over R squared. So that's simple enough. These two remaining terms here, this is the radial diffusion. So this is the diffusive part of your dynamo equation. Remember, you just have changes in the magnetic field have two contributions. One is what we call the dynamo term. It's called U cross B. The second part is the diffusive part, and that scales like 1 over magnetic field. So these two terms are then the spectral representation of this diffusive part. And what we have left on the right-hand side is now the nonlinear term. It's the dynamo term. So that's the term called U cross B. And actually, as we said, we just want a colloidal equation here. So we multiply this with the radial. So we just take the radial component of that. And then we also just want the spherical harmonic, so the contribution to the spherical harmonic degree L and M. Okay, so still parse work. So the additional part to screen that out is then you actually, as I said, to multiply from the left-hand side with PLM and with e to the minus im phi, right? And then to integrate over a spherical surface, so pi from 0 to 2 pi, and then basically the cos theta from -1 to 1, right? And this would then give you this. That's actually what it says here, where the omega is now just this surface part integral. So it contains the d phi integration and the theta integration. Just another expression. Okay, so this is now the spectral colloidal equation, magnetic colloidal equation. And well, the important part now is to solve this nonlinear term. I mean, this, I have told you what this actually is. So this looks pretty easy, but this we still have to solve. And as I told you, solving these terms is a major part of the problem. And as I already said, they are calculated on the grid. So in this case, we want to look at call U cross B. So we first calculate U cross B. And that's sometimes called an electromotive force in mean field dynamos, but it doesn't matter here. So, and then we need two components of this, basically the theta and the phi component, and they're just given by these simple combinations of velocity component and magnetic field component. So basically, this is what we need, as I've written down here. This is then just this, right? And you start with basically calculating, so just calculating these terms on the grid. So this is easy to do. So you have the magnetic field on the grid, you have the flow on the grid, you just multiply it. And then you have these products on the grid. And then the next step is you need a spherical harmonic representation. So you have to transform to the spherical harmonic space of this once you have a grid representation. Again, just doing this exercise. basically. Right? And then once you've done that, you can calculate this extra derivatives. As I said, for the derivatives, we always use the spectral space. So transform this. So if you first multiply on the grid, and you transform this to spectral space, then you take this extra derivatives, and then you know analytically what this guy is. Right? So this is just now writing this derivatives in terms of the spectral representation. So that's how we do it in the code. Now we have all terms we need for the colloidal magnetic equation in spectral space. Right? So how does it look like in the code? So that's the next question. So let's have a look into the code. And should we start from the beginning? So we start with magic.f90. Okay. So the main program is called Magic. You may have guessed that, right? So it's magic.f90. I will open it for you. So we start with a lot of explanation. So in case you forgot what different parameters mean and how you control the code, it's also explained a little bit, at least in there. Then you load several modules, the variables you need actually, and then you define a few more, and then here's some compiler instructions actually.
Can everyone see this?
Then you initialize your MPI parallelization here. Okay, and then you have to go further down. And then at some point you just call, so this is now, go further, okay, so this is now still the ramp up part, as I call it. So you define a lot of stuff, and then at some point you read the name list that you have provided. So this is done with this subroutine. And then you initialize some output. So once you know the parameters, you can calculate a lot of arrays that you need later on. And then, well, additionally, you check the truncation. So in case you provided a truncation which doesn't make sense, that's checked here. So what does it mean a truncation doesn't make sense? So I guess you all know that if you want to use fast Fourier transforms, you have to use, number of grid points which is 2 to the power of something, right? So that would be a restriction. I mean, Magic is a bit more clever.
Or 3 or 5.
You can also use factors of 3 or 5. So basically, what Magic, the number of grid points Magic can use is, say, 2 to the alpha times 3 to the beta times 5 to the gamma. Well, alpha to the gamma could be anything. But still, this is a restriction, right? So you cannot express any integer with that. So this is, for example, checked. Also, the number of radial grid points, -1 needs to be the number of MPI ranks. Or a multiple of that number, MPI ranks, so that we can run it efficiently in parallel, in MPI parallelism. Because the MPI parallelism at the moment works just on the radial direction. So therefore, for example, yeah, and another restriction for the radial is that you use this fast Fourier transform also in radius, right? So because you use the Chebyshev polynomials, and this ends up being cosines, and so then that means the radial grid you can use is also restricted. And actually, the numbers you can use, they're given in the manual, but also in the code actually, and it's checked. Provide that correct number, so you don't have to worry for that. Okay, and then this was the check truncation, and then we open some output files that we want to write in later on, and then, well, here a lot of information is written, as I said, in the log file. So all the steps you're going here are documented in the log file. And then going further, then you have to initialize a lot of stuff. So, for example, radial functions, for example, that you need. So, for example, the radius itself. So first you have to calculate the grid points you need, right? And then you calculate, for example, what is 1 over r squared, because you need that frequency and some other arrays frequently. And then you also have the same basically for the horizontal dependencies. I guess this is now in here, right, Thomas?
Yes.
LM, so this tells you there's something to do with the straight harmonic representation. So these CLMs, for example.
No, this is for the MPI domain.
Oh, this is for the M. So where's the horizontal?
Horizontal is just in the pre-calc, I think.
So it's somewhere in here. So you have something which is does the same, not in radial direction, but for any functions that depend on longitude, latitude.
The pre-calc. So after that,
okay, so it's part of that.
Because here it's just the allocation of most of the allocation of the memory actually.
Okay, so go further down and get.
Yeah, pre-calc is here. So once you finish allocating the whole memory required by the code, then you can start to do some pre-calculation.
Yes.
And
So it calculates, for example, these coefficients that you need to calculate the derivative, right, and other stuff as well that you need later on. Okay, go further. Okay, more initialization, and then you write named lists actually in the standard output because you want to do that, and also in the log files you can remember everything that you used here, all the parameters, and then here is the get start field. So this is when you read the restart field or you initialize it somehow, right? This is done by this routine, and then there is more pre-calculations here. So this actually calculates specific times. So you can actually tell Magic when you want specific output. You can either say, I want, for example, a G file every 1,000 timestamps. Or what we did so far is you told Magic, I wanted 3 G files in total. Right? But you can also provide specific times where you would want that, which is very handy. For example, say you have a run that you did a run before, and you want to know, well, but you didn't store G files or anything. And then after looking into the run, you realize something strange is happening at this and this time. So for example, there's a peak in kinetic energy, whatever. Then you may want to rerun that run, and in this specific time, you want to have a G file to look at the solution. And you can specify this in Magic. And then this actually looks at all these times that you specify and then stores them. And then Magic knows, okay, at these times I have to do something. Okay, we can go further. Step time. So this is now the workflow. This is the actual time step. Right? Okay, you can briefly look into this. Okay.
You sure you want to do that?
I haven't done it for a while, so maybe it's too wild now. I don't know.
Well,
surprise me.
Yeah, forget about that.
Forget about it. So it's not really doing anything, right? Initialize
well,
stuff.
It's just allocating here.
Yeah. So does it actually call something?
Yeah.
But you have to scroll down a lot.
Yeah, this is barrier. Yeah.
Okay.
Yeah, here. Yeah. Well, but
yeah. Okay, so it's a little bit complicated because of the parallelism. Yeah. So here, this probably has to do with the radial parallelism. So
it's transposing the domain from R to L.
Yeah.
And to R. Yeah. Actually, yeah, it's because the restart file is stored in L, so you have to redistribute it in the radial.
So this is just a redistribution. Do we call something like the radial loop here?
Yes,
Later on. Okay. I mean, you can say something if you think something is important here. So you see that there is a lot of stuff, because you have to define stuff, you have to allocate stuff, you have to distribute stuff over the processors and so forth. So it's a lot of overhead. And then basically here, there is again something useful. And this is called radial loop G. So this is now actually the calculation of the nonlinear terms in this subroutine. And this is done, as I said, for every radius independently. So these equations are then independent of the radius. So you can calculate this for each radius independently, and that's done here in this radial loop G. Now, do we want to look at radial loop G?
No, we don't.
Because then I have here, it's empty? Okay, but I have here a little bit. So, okay, in radial loop G, you call basically a lot of other subroutines, which actually then do the work. And and basically this shows you the first work that is actually done. So you start with going into this with a spectral representation. And you want to transform. So at a given radius, you know all the fields. So in the restart files, what you store is all the fields for all the radial grid points, but in a spectral representation. And we call this in the code, we call it here basically, for example, it's a two-dimensional array, and it's called G, R, L, or that's the other way around. Let's call it, it doesn't matter. So, as I say, and this LM actually now, think of this as number and all the different spherical harmonics modes you can have. And you have this for each radial grid point. This is how it's stored in the restart file and how it's actually read. And then you want to now transform this on the grid. And as I said, there are two steps involved. One is the fast Fourier transform, and one is the Legendre transform. The Legendre transform is shown here. So you have to step over all basically degrees and orders, right? And that's basically these two loops doing that here. So I start with choosing actually n degree, MC it's called here, and then I step over all orders that I need for this specific degree, and then I sum basically all spherical harmonic representation. So, and here is one example where I calculate the radial velocity, VR. And this is just the equatorial symmetric part. And I also calculate the antisymmetric part later, but that's just showing you the general idea of it. So this is how I calculate it. So it's just some coefficient multiplying it with the PLM, the spherical harmonics. And this coefficient now it's called DLHW, and it's, well, we have complex data definitions here, so this is kind of object oriented. So this is stored in like helper, and this is the specific object stored in the like helper. And what that means is basically the DLHW is L, this famous L times L plus 1 over R squared. That's what it is.
Times W.
And plus the W itself. So plus the polarity potential at degree and order, and yeah, LM and at the given radius. So this is now the factor you need to calculate actually the radial field, right? So this is the prefactor you need in the spectral space. So this is now the radial magnetic field on a grid point in the latitudinal grid called MC. So this is this specific grid point. And then the last step you have to do is you have to do the Fourier transform to get from the specific harmonic order to the longitude. So these two parts you always need. And this is, as I said, it's a standard FMC, and there are different libraries available to choose between. So now, by doing these two steps, you go.
Well, you can just mention that the CMake, when you compile it, tries to find the most appropriate library you might have on your machine. So by default, it's trying to link with a mass kernel library from Intel, which is supposed to be, which is actually faster than the built-in library. But in case it doesn't find it,
Then it will try to use built-in FFTs from Magic that
Yeah, so
are
we
slower, but don't need any external library.
Yeah, Magic can run independently if you want.
Right.
May not be the most efficient way. So the MKL can be like 10% faster or something, but if you don't have it available or you don't want it, you can run it Magic independently.
And also we can think about plugging FFTW or different libraries there. It should be easy to change it the way it's done.
Okay, so now you have the velocity field, as an example, the radial velocity field on the grid. And you do the same with all the other fields you want to have on the grid. And what you want to do is now you have these now on the grid, and then you want to calculate this on the grid. And this is now shown here, so it's a get and L. So in get and L, you actually get the nonlinear and L stands for nonlinear. And this is now very simple. So you just step through the grid, and you step through the theta grid points, and this is done in certain blocks. So you first take, let's say, the first 10 theta grid points, and the next 10, and so forth. And so n theta just numbers the grid point, and then n phi the latitudinal grid points, n phi numbers the longitudinal grid points. So this is now actually the v cross b and the theta component of it. So this is what we needed. Remember, the v cross b or u cross b. I wrote here in the code. It's called v cross b, and then there's the theta component, and that's just the product of the phi component of the velocity field, this here, radial component of the magnetic field, this here, minus this, the radial component of the velocity field times the phi component of the magnetic field. So this is how this term, the theta component of u cross b, is calculated. So now you have this nonlinear term on the grid. Next step is you take these extra derivatives.
We get TD. We need to get TD. Yeah. Well, you can show it.
It's here. It's here. I have it here.
Okay.
You can show it as well. So now you remember, if I want to have the curl u cross b, this is the spectral representation of it, I need the additional derivatives. So this curl, and we want to express it in analytical spherical harmonic representation. So we just have to use different combinations so that there is this recurrence relation, right? So we have calculated this f now, this f phi and this f theta, and they're called v cross b phi and v cross b theta. So p stands for phi and t for theta, and lm now tells you this is the spherical harmonic representation. So what we did is, this is the step I've forgotten. So after we calculated this actually on the grid, right? Phi theta. And then we want to transform this now back to the spherical harmonic grid, because there we can take the derivatives, and that's explained here. And this is in Legendre underscore spec underscore 2 underscore grid, but you don't have to go there. I think it's too confusing. So what we do is now the back transform, and you remember the back transform was the Gauss-Legendre integration for the longitudinal, for the latitudinal transform. So this is done here. So you actually take the weighted Legendre polynomial. So these are the Legendre polynomials times the Gaussian weight, and you just multiply this with this F1ES, and this just contains the field I've shown before. It's called in a different way because we have suspected actually certain components that we needed here. So that's a bit confusing. But this is basically now these fields here are part of these fields that we treat here. So, and then basically you do this sum over theta, and then you did actually the Legendre transform, Gaussian Legendre transform. That means now you're in a space where you have the different spherical harmonic degrees, but you still have it on the phi grid, so on the longitudinal grid. So the last step you need is for these, you need the FFT and phi. So this is now the back transform. Remember, we started with the spherical harmonic representation for the individual fields. Then we calculated, we transformed on the grid the individual fields. We calculated the components of the fields. We multiplied them, and now we transform back this nonlinear terms, and now we are back in spectral space. And then once we're back in space, spectral space, actually you can do these additional derivatives analytically. We're just multiplying with this, basically these factors, and they are called d theta 1s and so forth, because they actually do the theta derivatives in this case. And then d phi is basically this term, which is doing the phi derivative for you. Okay. And now, so this is the nonlinear term. I hope you're not asleep by now, but let's go through it once. So this is now the nonlinear term in spectral space that you need for the radial colloidal magnetic equation. Okay. And we call this dB dt. And for some reason. Okay. So it's called dB dt, and this gives now the spectral representation for one specific mode and one specific radial grid point that we number with. So now we're set. We have everything we need for this equation. We have calculated this part, so that's basically what we just calculated. And we call it NLMG here, or on the menu it's called this one, the nonlinear dynamo term. Okay. So now you realize that all the special derivatives are gone, and we know all this in spectral space. So the last thing we have to deal with is actually this time step. So this is something we also have to discretize, right? Okay, that's the next step. Okay, so this is what we just did. So we calculated it on the grid at the nonlinear term, and we transformed back. So now we have everything for the spectral equation, and then we want to do the time step. And as I said yesterday, we are actually using the mixed implicit explicit time step. And generally, you can think of it this way. So think you want to integrate a variable x in time. Right? So you want to know the time derivative to solve this integrate in time, and then you have something which you call the implicit part that you want to integrate implicitly in time. And you have some terms that we call the explicit part here that we want to integrate explicitly in time. So, and for the implicit time step, we use the Frank-Nicholson method. This is shown here. So now this is this time step here. So this is the discretization of that time step. Right. So now difference at time t plus delta t minus x of t over delta t. So this is the time step, and now this contribution to this time step from this implicit part is this. So it's just, well, basically the information I, or these terms I at the time t plus delta t, weighted with the weight alpha, and then the information from the last time step, or for the current time step, weighted with, well, one minus alpha. So this is the guess of it. So you want to know the x at time t plus delta t, and with an implicit time step, you also use these terms at time x plus delta t, right? And these from the last time step. Now, this is what we do for this term. For the explicit term, time step term, we use the Aaron-Bashworth type, which gives you this. So it uses, to get this x of t plus delta t, uses information from the current time step and the previous time step, t minus delta. And then you can calculate the x of t plus delta t, so the next time step, basically. And while the alpha, typically for Crank-Nicholson, it's half. So that basically this time and this time have the same weight. And then Crank-Nicholson is of second order. We use alpha 0.6 most of the time. And why? We don't know. Well, this goes back to Gary Glassman.
Yeah, a bald guy with a big beard.
Yeah, a bald guy with a big beard who's now building a log hut and is breeding cattle somewhere in the desert. So obviously, I mean, as I told you yesterday in the beginning, all this code goes back to a very old version of Wicked. That's why. And so obviously he played with this alpha, and he found that if you use 0.6 instead of 0.5, you can use a larger time step, and the code is more stable. In theory, that means your time step is not second order anymore. Right? It's only second order, strictly speaking, if alpha is 0.5. Okay, that may be bad, but it turns out it's not very bad. The reason may be that you have to solve. Well, you can always. So if you go from second order to first order, you can reach the same precision if you choose a smaller time step delta, right? Then you can compensate. But generally, you don't want to do that, right? Because that costs time in your time integration. But of course, you have other factors which also determine the time step. So if these other factors, like very strong forces or rotation in your system, forces you to use a very small time step anyway, then choosing 0.6 for alpha instead of 0.5 doesn't matter much. And for some reason, it gives you a more stable code. That's what he said and published, right? And nobody knows why. I mean, that has to do, I think, also with a specific problem you're looking at. So actually, we tested that. I tested it some time ago. I didn't find a difference. 0.5 or 0.6, it doesn't matter. There's no degradation in precision or whatever. And the time step is also not much different. So I did this for a few test cases. I couldn't find any impact, but for other test cases, it may be true. So usually we stick with 0.6 because of Gary. Right, but at the end, I think it doesn't matter much. So if you feel more comfortable with 0.5, do it. So no problem. So now, but we want to through both time steps together to get this equation, and then basically, if you do that, you end up with an equation like this. And on the left-hand side, I have now basically done everything for the forecast, basically. So think we are now at time step t, where we know the field of x. That's the present time step. So we know that field. We also know we can calculate this, we can calculate that, and we know the field from the last time step. So this part basically is known, and then this is the forecast part. So this is actually the update of our system that we want to calculate based on this. And this typically we call the right-hand side, and this we call the time stepping part of the time stepping matrix. And specifically, it then looks like this for now the spectral representation of the magnetic colloidal potential G. So the equation looks like this. So there are two matrices, A, Kn plus alpha. This is the weight again from the Crank-Nichols times the implicit part Kn. And Kn actually means, again, what I told you before, K numbers the radial grid point. So we have basically one equation for each radial grid point. And then the n is the Chebyshev polynomial, so your number over all Chebyshev polynomials. And well, and then the right-hand side looks like this. So it's A again appearing in I, and then the explicit part like this. It's the Adam Bashford weights here. And then you can look at what these matrices have to be. Again, this is just screening out the radial part of your magnetic field, and this is now just dividing. But this is actually not the time step. And this is the Chebyshev polynomial here, and the I now. So this, remember, this is the implicit time step. So this is now just diffusion for this case. This we treat diffusion implicitly, and explicitly we treat just the nonlinear term. I've shown you how to calculate this. So here, basically, all this is known. So we can construct this matrix. All of this is known, right? So everything is pre-computed. And we know also this, because we know the field in the present time step, the last time step. So we know basically the right-hand side, or I can go back here. We know that side, we know that side. And that just gives you a simple linear system of equations. And it's an equation for each radial grid point. And this is all just for one spherical harmonic mode, L and M, right? Now you have one equation for each radial grid point. And the unknowns are now the Chebyshev polynomials. Right? So these are the unknowns, and then you combine all radial grid points equation to actually solve the system for all these unknowns. And obviously, you need as many radial grid point equations than Chebyshev polynomials, and then you can solve the system of equation. And it's a simple algebraic system. We simply do LU decomposition, so very standard method, boring method, which just turn out to be efficient and solve this linear system. That's a very easy step. Good. How are we doing in time, Matthew? 15 minutes. Okay. Should we look into the code again? You care to look into code, how the time step is done? Well, maybe we can do it briefly. So now this is this part which we call the update. So you want to go to time step to time ti plus 1 from time ti, which is present time, and then dt. This was the WT. So you want to update your field. You want to know what is my field at time ti plus 1. And then, so this is the block we're looking at now, and well, now we have to look into the code again. If you want to do this, we look at update B. Yeah, so let me just, we can start with defining some stuff. So in the code, how are the different parts called in the code? So I already told you that this nonlinear term, which we treat explicitly in the code, that this is called dBdt. This is how we ended up with when I showed you how to calculate the nonlinear term. Then this what we call the time stepping matrix is just this matrix. So this is the matrix here, right, in front of this unknown coefficients we want to solve for. So this is just this matrix, and we call it BMAT. Now, Anke actually shows here how BMAT is calculated. So BMAT is just the sum of these two contributions, and we can look at here's the AKN, for example. This is, well, it's written this way. I come back to that. So it's just I come back to that. So that's basically shown here, but you can leave that on the screen. And then we have something which we call dBdt loss, which is in a way the counterpart of that, but that's now just on the right-hand side. So this is from the previous time step, the explicit part from the previous time step, and the implicit part from the current time step. So this is something which is known. And then we introduced two different ways, actually, and then we introduced this. So one ODT is a variable we pre-calculate that's called O underscore dt here. This is 1 over delta t. And then this is this famous L times L plus 1. This is this one, DLH. And then OR2 is also pre-calculated. This is 1 over R squared. And then we have the Chebyshev polynomials, which we also need here. These are called Cheb. And then this is basically this. Well, yeah, this is this part here, the AKN, right? Yes. This part here. And then you also have this explicit part. This is the diffusion part, which is so the implicit part is just the diffusion, and this is this part. Okay, and here I have now how the right-hand side is calculated, and this is, well, this now needs all these different parts that I just defined before. So dBdt times weight 1, dBdt loss times weight 2, and so forth. It's just the way how we express it in the code, and then we call it the right-hand side. And as I said, you end up with an algebraic system of equations for a given degree and order L and M, and and you do this for all different radial grid points K, and then you solve the whole system for all the to get all the Chebyshev polynomials. So you end up with B. B is now, or G is called B in the code, right? At time I plus 1. So this, if you solve the system, this is what you get. Chebyshev representation for all spherical harmonics, right? So, and this is done on the update B that an update BF90 that Anke has on the screen here. And then basically here I show again how the right-hand sides are calculated, and Anke has it here on the screen. So, okay. Yeah, and how we solve the linear of equations, there's a standard method, as I said, called CGAS or ML. You can find this in numerical recipes. It's very standard, but still very efficient. Okay, and then basically the last step in this routine is how you calculate this dB/dt last. It's called last because that contains the information from the previous time step. So you're going to need this for the next time step as well. You calculate it here, you store, and you reuse it for the next time step. So that's basically it. What I haven't told you is what's with the boundary conditions. So I've shown you, so we derive an equation, for example, a dynamo equation for each radial grid point, a spectral equation, and then we solve it. And then we have the result. But where do the boundary conditions come in? So does anybody know how that works? Well, I mean, generally there are basically two ways of doing it. One way is, or two ways I can think of. One way is you choose ansatz functions, which automatically fulfill the boundary conditions. For example, you can choose cosine functions, which become just one at the boundary side, so they have a predefined value at the boundary. So you can just use cosine in radius, cosine ansatz functions, you would have a result which has a predefined value 1 at the boundaries, right? So that would be one option. That's not what we use, of course, but so what we do is we basically derive all these equations, but then we don't use these equations for the outer grid points, but we replace it with the boundary conditions. So, for example, the equation for the very outer radial grid point, which we call grid point 1 for some reason, we go from the outer to the inner. Here we last one. Still in here. So you replace this equation with basically the spectral equation for the boundary condition. And I don't think I have that. No, I don't have that. I basically gave you an idea yesterday that you can define a spectral equation for the boundary condition as well. We talked about this yesterday. So that's what we do. We do this for the very first radial grid point, which is the outer boundary, and we do this for the very last radial grid point, which is the inner. Now, it's a bit more complicated if you have a conducting inner core, because then basically you have a solution in the outer part where you have flow producing magnetic field, and you have a solution in the inner core where it's just diffusing. So basically, you match these two solutions with some matching conditions, which are simply that the field has to be continuous at the interface, and then you solve the coupled system of equation. Coupled, we add this radial grid point. They share the radial grid point, which is the inner core boundary, and there they're coupled. So you have basically two coupled systems of the kind I've just shown. Yeah, this is basically how it works in the code. A pretty rough idea, but I think we've talked about all of the methods, or most of them at least. Yesterday I briefly mentioned also that time step is adaptive. So you have to be a little bit careful, which means, for example, let's look at these matrices again, this matrix A, for example. So you compute this at some point in time, and you can actually keep that matrix constant. Yeah, it just depends on the Chebyshev polynomials, not on any of your variables, but it depends on the time step delta t. So if you change the time step, then you have to recalculate these matrices, and you also have to redo the LU decomposition. So that's each time you update this time step, your time step becomes more expensive. And actually, Magic tells you when it's doing that. So maybe you've looked at your log files, and then it tells you, okay, I have to change the time step. And if you would time this, you would find that if you do this, it takes significantly longer. Right? So So it's a good idea to choose the time step such that you don't have to update the time step more frequently. And you do this by choosing a time step which is already small enough. Right? So then, otherwise the system would oscillate a little bit about the time step it needs according to the Cohen-Friedrich-Levy criteria. So at one time step, it would say, okay, the time step is a little bit, I could make it a little bit larger. So I make it a little bit larger. So I recalculate this matrices. And then at the next time step, the velocities become a bit faster. And then it says, okay, but I have to make it a bit smaller again. Right? So it oscillates basically around that. And you avoid this by setting the dt max, so the maximum time step, a little bit lower than this limit. So do you know what that limit is? Well, tomorrow we'll tell you a little bit about that. Basically, you don't know it in advance, right? But you have a rough idea. For example, the rotation time of your system is a good guess, for example, right? So you want to solve the rotation time of your system. You want to resolve that. So anything happen on that rotation time, and to resolve anything happen on that, you need a time step which is 10 times smaller or something at least, right? So that's a good first guess. But then you should still look at your solution and actually into the log file whether it frequently updates the time step or not. If it does frequently update, for the next run, please choose somewhat smaller time step by adjusting dt max. Okay? So that was about time stepping. Some people are interested in the Coriolis force. The Coriolis force in theory is linear. It's just U cross rotation, right? So we nevertheless treat it explicitly. So it moves on the right-hand side. Why? Because the Coriolis force has extra derivatives in there. And when you do the extra derivatives, you couple different spherical harmonic modes. So you remember the theta derivative, right? That coupled a spherical harmonic mode L to the mode L plus 1 and L minus 1. So the Coriolis force couples all spherical harmonic degrees. What we do in the moment in the code is we solve for each spherical harmonic L and M, we solve one equation. And that gives us all the Chebyshev harmonics. Right? If you would treat the Coriolis force implicitly, we would have to take this coupling into account. So that means we would have to couple all degrees. Get a huge matrix, which we then have to invert, instead of a lot of small matrices. That's why we keep the Coriolis force explicitly. That means we take the Coriolis force, put it on the right hand, from the last time, so put it on the right hand side, and then just calculate what is the contribution to the specific degree and order you want to solve for. That's why we do it. In theory, so generally what you can say is if you choose something implicitly, you can choose a larger time step. Because implicitly is better because you take the information from the time step you want to predict, right? That's better, certainly. You don't take the old information, you take also the current, the new information. So there, generally, the saying is you can choose a larger time step. But you have to pay for that. You get just much larger matrices to invert. So it's cheaper to keep the time step a bit smaller, but to solve for a lot of small matrices instead of a large matrix, right? So that's why we do it. People have played with that a little bit. People have tried to use Coriolis force implicitly. For example, Gary Glatzmeyer did that. And what he said is, yeah, sometimes it pays off and everything becomes a little bit faster. But if your radial number is large, then your flow becomes so fast that the Cohen-Friedrich-Levy forces a small time step anyway. Or the Lorentz forces become so strong that the Cohen-Friedrich-Levy forces a small time step anyway. So by teaching the Coriolis force implicitly, in theory, I could choose a larger time step, but then other conditions, Cohen-Friedrich-Levy, force me to choose a small time step anyway, so you don't gain anything. So that's why we still have Coriolis force explicitly. Tomorrow wants to check that again. So
Yeah, it's just that I think when you tested it was like.
Yeah, that's a long time ago.
But in the special parameter regime,
So
that's not even relative on Rand uses already more less restricted than what you did at this stage. But I suppose that low X-band number might pay off much more than what you did.
that could be. So that's something that is maybe worth testing. Still plan to do that, but we'll see. Yeah. Okay, so this is what I wanted to tell you about the numerical method. And so, do you have questions? And
how do you take care in the restart files for the intersection? Do you store 2 time steps in one file?
so, how do we take care of that? That's a very good question that I didn't mention. So, what we do is in the restart file we store this. So it's not just the field itself, but we also store this, what we call dB/dt last, and this is the information you need for the next time step. So it includes this at time t minus delta t and this. Well, otherwise, the restart file would just be half as large. And we include this, of course, for all the fields we have to include that. That's right. Good question. More questions? It's not the case. Yeah, well, go ahead.
Is there, how do you advect things? What kind of advection scheme do you use? Do you use only this spectral space for advection?
Yeah, it's a very standard spectral space. Nothing special, like no downstream algorithm or whatever. It's really just directly in the spectral space. So this is just a normal nonlinear term that we calculate. There's nothing special to do about it.
Is there any reason why you use the lat long grid? You could use any other, right?
We could use any other, but as I said, I mean, the reason is that you have these efficient transforms for this grid.
So it's really those transforms that make it fast.
Yes, yes. And if you want, it's not a classical lat long grid because in latitude it's not really equidistant because well, it's a grid which is defined by the Gauss-Legendre integration. So that's a bit. It's not much different, but it's a little bit different. But that's important to get exact integration at that point.
Okay.
Yeah, but I mean, people that do find the differences, for example, and not this analytical derivatives that we do. They are free to choose their grids, right? But since we want to do these analytical derivatives and use the fast transforms to go back from spectral to grid space and from grid to spectral, we have to use that grid. There are ways of transforming the grid.
Yeah.
So you have additional factorial functions that you multiply, and these functions then you also have to calculate the derivative of this in vector spaces. But that gets a bit complicated. But in theory, you can do that. You can transform your grid and still
theoretically
keep
you
the
can
method.
transform to any grid, right?
Yes. Yes. And in radius, actually, we had this feature in there once. We tested it a little bit. There's just a cosine, so that's not so difficult to play with that.
Yeah.
So, more questions? Okay. If not, we could go for lunch or keep on playing with the code or whatever. Let me check the time. Yeah, it's just. So, Mensa?
Wo das ganz einfach geht. Ja, ja.
And I have to.
Hat er schon andere Möglichkeiten?
Yeah, actually, with this. can be automatic. So there are links. So we can, there is a dot via R and link it to
Wenn der Leitung ist.
Epsilon, that's why I called EMF here. So that's why for the EMF it's classical, it's the code. So I thought here it's not more complex. I changed.
Du kannst einfach, wenn du nur die Kontur, genau, du kannst hier, das zweite Ding ist ein Clip. Ein Slice ist, ja, ein Slice ist wirklich nur die Ebene, aber ein Clip ist, da kannst du nur ein Teil und ist dann noch so gemäht. Also kannst du hier dir die Hälfte wegklippen. Genau. So, zack, du hast einfach Apply, die Play-Stütze. Und jetzt sagst du einfach bei, kannst du die alle umhängen. Den Stream Tracer, klickst rechts, das Change Input, hängst den an Clip 1. Nee, du musst jetzt nicht so kaputt haben. Clip 1. Genau. Zack. Genau. Und die Konturen und so könntest du auch noch an diesem Clip hängen. Warum lädst du so aus? Ach so, du hast den Clip. Mach mal den Clip aus. Du hast gerade geschnitten. Ja, das müsstest du jetzt auch noch hinnehmen oder ausmachen. Jetzt von hinten. Mach mal Expert.
Ach so, man müsste mal von der Seite, wo wir die Karte haben, ne?
Ja,
Aber dann ist
das wird die sein.
Ach so, du siehst es halt nicht so genau.
Die Kugel noch da könnte wenigstens, man könnte die Kugel, man könnte die Opazität gleich alles in Ruhe sind. Ja, die transparent hochsetzen oder
Oh, gibt es ja auch extra so.
ja, der Opak heißt ja nicht, also ja,
Opak.
ja, aber du kannst nicht Opak heißen. Also,
Ich weiß nicht, aber alles, was man was auf seinem Fernsehen das wird immer auf Karte
So, Ankit, what is the method of choice to collect the data?
Yeah, perhaps just set the SCP and get your files to my directory. Yeah, that will take some time. I have to type the password 16 times.
Sorry.